Well, welcome. I'm Mrs. Oppold, and we are working on Section 1-1 today in AP Calculus AB. And just looking at the first page of your notes, if you do not have your notes, go ahead and print them. They are located in Schoology. Otherwise, you will be picking up a Unit 1 notes packet in the classroom. So, just a few things I want to point out before we get started on today's lesson. You're going to notice a few things about my note sheet, and that is in the header. It's going to talk to you about what topic we're studying. We're looking at 1-1 today. It'll describe what it is. We're going to talk about can change occur at an instant. And in the left here, there's always going to be a couple things that talk about what is our big idea? What's the overarching idea that I'm trying to get across to you today? Today is all about change. And so there's kind of three large topics when we're looking at AP Calculus. We can talk about change, we can talk about functions, or we can talk about limits. Well, Unit 1 is labeled limits, so we will be talking about limits a lot in this chapter. But today it's all about change. The other thing you notice is you're seeing in number 2, that corresponds to the mathematical practices. And the mathematical practices connect representations is what we're focusing on today. In the AP test, they will be looking for all 4 ideas. Can you implement? Can you do procedures? Can you do algebraic notation or calculations? And mainly, can you do the calculus notations? Can you connect representations? Can you connect concepts? Justification is part of that, connecting concepts, but can you justify why something is true? And then lastly, being able to communicate mathematically and writing mathematical notation precisely. These are big topics for AP Calc, and you're going to find that the rigor level is quite high and the expectations are going to be high because we want to set you up to be ready for college, especially if you're going to skip over Calc 1 because you're going to pass the AP test. All right, so let's just get started. I'm on a page ahead, and this one says, think about it. So I'm in my car, I live in Hastings, and I want to know, what is my average velocity as I go home? And home for me is in Mapleton, Minnesota. Mapleton, Minnesota, as you can see, is south of Hastings. And so I kind of take Highway 47, get myself into Northfield. Sometimes I take the back way from Northfield to Faribault, and from Faribault I can kind of either jot over to Mankato and down Highway 22, but sometimes I also stay on the more interesting roads like Highway 60, and then start taking a bunch of county roads. Stay on pavement, but I take the county roads and zigzag my way down to Mapleton, where I grew up. Now, from my house in Hastings to my dad's driveway, it's 99.7 miles. And it takes me almost exactly 2 hours to get there. So what would be my average velocity? Oh, you're thinking about distance equals rate times time. Good idea. Well, I can figure out the rate by going distance divided by time, correct? And the distance, so I'm going to call my rate, oh, that's not writing well. Let's try again here. I'm going to call my rate the average velocity. And the average velocity is going to be 99.7 miles divided by, let's use labels, that's always a good idea, divided by 2 hours. And then we see that we get miles per hour, which is a velocity label. If I divide that in 2, I have it on my calculator. Let me bring that up. 99.7 divided by 2 is 49.85. 49.85 miles per hour. So, question. That we said is an average velocity. Am I always going 49.85 miles per hour? Or maybe sometimes I'm going 55 miles an hour. And then sometimes I'm going maybe 30 miles an hour. Because what assumptions could you make about my driving? Well, looking at the map here, I see that there are some small towns that I pass through. I definitely have some stop signs. all these things, sometimes I travel so that I'm on the interstate where I can go 70 or 75 miles an hour. So all these things influence, don't they, my rate that I'm traveling. So we're just talking about the average rate there. Let's move ahead. This next screen, it jumped to, hang on. This next screen says, suppose a ball is dropped from the top story of the Burj Khalifa building. It's the tallest building in the world. It is located in Dubai. It's around 2,700 feet tall, which roughly, if a mile is 5,380 feet, it's roughly a half mile in the air. Find the velocity after 5 seconds if we drop this ball. Well, this is asking us for a velocity at a precise moment, and we talk about that being at an instant. So by conducting experiments in the late 1500s from atop the Leaning Tower of Pisa, Galileo discovered that the distance traveled by a freely falling object is directly proportional to the square of the time it has been falling. In this case, the distance the ball has fallen, s of t, after t seconds can be given by the equation s of t equals 16t squared, kind of our equation from Galileo. We can compute the instantaneous velocity at 5 by computing the average velocity over a really short period of time. Now, when we did my average velocity to Mapleton, we did it over a 2-hour spread of time, right? If I bring that time frame in, I'm going to get closer to an instant. Maybe I do it over a 1-minute period. Maybe I do it over a 30-second time frame, or lessen it and lessen it. And then I can get more to what an instant of time is. Because we know that slope is equal to what? y2 minus y1 over x2 minus x1, which really, if I have miles on top, hours on bottom, that slope, that rate of change is going to represent my velocity. But I want it to be at 5. So how do I get this to be just 5 minus 5? Well, that would give me a 0 on the bottom, wouldn't it? This is tricky. This is where calculus is going to come in really handy as we move forward. Right now, we've got to kind of figure out a way around getting the instantaneous velocity the best that we can. We're going to use the average velocity. So using your calculator, I want you to obtain 3 other estimates that are progressively more accurate for the instantaneous velocity at time 5. We know we can compute the distance traveled like at 5 seconds, 5.1 seconds, 5.01 seconds. And so I can use distance over time to get velocity. All right, so quick tutorial. You probably know your calculator very well, and you're going to get to know it even better this year. I'll show you some new tricks and things, and then you'll pick up some calculus ideas as well. Some functions that you've never used before. So I'm going to go into my y equals, and I'm going to put in 16 x squared, because I wanted to calculate the distance traveled over a time frame. And then I'm going to go back to my home screen. Second quit will always bring me back to home screen. I'll hit clear right now. And this little tidbit of information says, you can put your equation in y1. We did that. Go to the home screen, hit alpha trace, and select y1. I want to bring up that equation that is stored in y1. Then I'm going to ask the calculator. It says, ask the calculator what happens at 5.1. All right, so alpha is the green key. Trace. I want to grab the y1 because that's where I stored my equation. Put a parenthesis in there. So I'm going to hit parenthesis. And let's see, we got to calculate it at 5 anyway. I'm going to put y sub 1 of 5. It's like function notation. What's my function evaluated at 5? That would be 400. So I'm going to write 400 right here. And then let's do 5.1. So I'm going to do alpha, trace, enter, parenthesis, 5.1. And hit enter. That gives me 416.16. Use all those decimal points. You'll hear it for the first time today. We go to 3 decimal places of accuracy in AP Calculus all the time, never questioned. So the most accurate I got right now is 2 decimal places because this was a terminating decimal. So I'll take it. And then, while we're on it, let's go ahead and calculate 5.01. So once again, alpha, trace, y1 is where I want to work. Get a parenthesis, and I need 5.01, enter, 4016016. Now I said in AP Calculus we always go to 3 decimal places. That's for our final answer. So if I have more decimal places in the intermediate work, I'm going to keep those extra decimals. Then, I see there's one more. Let's do alpha, trace, get the y1, function, parenthesis it, 5.001, and enter. You'll notice you do not have to close parentheses on our calculator. The programming language is such that it is not necessary to close it. So often you'll see that I don't take that time to close it. So at time 5.001, I'm coming up with 400.160016. And I'm going to have to rewrite that one. Okay, lots of accuracy. What I would like you to do is go through and calculate the slope between 2 time frames. So I'm going to look between 5 and 5.01 and get an answer right here. Okay, so what will that look like? Well, I need to calculate a slope. Let me silence my phone. It's going crazy. So I need the distance, the change in distance over the change in time. So I'm going to go, we were 5.1. 5.1, I want to copy that. I guess I got to go this way. I want to copy that, so I'm going to hit enter, and I want to subtract the 400. Enter that. That gives me the distance traveled. And then I want to take that and divide it by the time change, which we can see the time change to be 0.1. So I'm going to divide this by 0.1. And this will give me the average velocity. Sweet. And I came up with 161.6 and feet per second. Okay. Now, what if I wanted to get more accurate? Well, then I need to have, we had from 5, I'm trying to draw like a number line, to 5.1. And we had a change of time, change of t was 0.1. What if I reduced that down? What if I went to 5.01? Okay, 5.01 gets closer to 5, doesn't it? 5.01. Now my change of time has decreased to 1/100th of a time frame. So I would take let me go grab the 5.01, which is still showing up on my screen, thankfully. I want that one. Ooh, where's my cursor? Lost it. That one, subtract the S of 5, which is 400. Okay, so now I've got 1.6016, and I'm going to divide it by the change of time. The change of time between these two is 0.01. So 0.01, and I'm at 160.16 feet per second. All right, might as well go the one last step. I want to copy and paste. I want that 5.001 distance traveled. Boom. Subtract the distance traveled for 5 seconds, which was 400. Boom. Distance traveled is that. Now, if I am at 5.001 minus 5, my change in time is now not 0.01, but 0.001, right? So I'm going to divide by 0.001. And I'm getting 160.016 feet per second. And people could keep saying, I can get more accurate than that, because you would just get yourself closer and closer to 5, right? And use that slope formula to calculate out an average rate of change, which is going to become close to an instantaneous rate of change, because now we're talking about the difference between 5.001 seconds and 5 seconds, right? And so that slope is getting closer and closer to the actual rate of change at exactly 5 seconds. So this is just a nice introductory idea to what instantaneous rate of change is talking about. Okay, so an AP question for you. From 2018, the AB question number 4 in the free response section, where you write out your answers, ask this. It says, the height of a tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. Part A, use the data in the table to estimate h apostrophe of 6. That's notation you don't know yet, but you will soon. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. So there's some things that you don't know, and you're probably like, why is she doing this to me? You're probably like, what the heck did that mean? Twice differentiable. It'll mean stuff when we get into chapter 2, so don't get too worried about it. They're talking about a function here, and we're also then talking about a different function, because the notation's different, isn't it? A different function. This is called a derivative. The h prime is how we say it, is a derivative in math, which talks about instantaneous rate of change. So it wants us to find the instantaneous rate of change at time 6, but the best I can do is interpret the meaning of h prime in this problem. All right, so I'm going to do a couple things differently. First off, I'm going to calculate out h prime of 6. And h prime of 6, I'm going to use the data to estimate it. That was one of the first things it asked us to do. And we're going to do it just like we did the last time. I'm going to choose the smallest time frame I can, around 6. So in my table, I see time 5 and time 7. That means that time 6 slides in between there. So I'm going to use those two, and I'm going to look at h of 7 minus h at time 5. The height at time 7 minus the height at time 5 will give me the change of height, right? Which is going to be measured in meters as described in the write-up. And on the bottom, I'm going to use the two time frames, the change of 7 minus 5. This will be the change of time. I could have put little t. I just gave you a little bit more to go on. This will be in, not seconds, in years. it would be difficult to notice the change in a tree in seconds, right? In a year, maybe we can detect it. All right, so we got change of height over change of time, and I've got to put in the numbers. I need a little more space. So I'm going to have the height at 7 years was 11. The height at 5 years was 6. Divided by 7 minus 5 is 2. And that's going to give me a 5 divided by 2. If you'd rather call it 2.5, you go right ahead and do that. 2.5 meters per year. Remember, we were talking about height. So this tree, on average, at year 6, averages or estimating 2.5 meters per year. Interpret the meaning. Well, we kind of just described that. You know what? Unit labels will help us immensely, won't it? This is the rate at which we expect the tree to grow at year 6 will be 2.5 meters. All right. So that gives you just a little flavor of what AP Calculus questions look like. They often have you interpret. That gets back to that communicating math idea. And notice all the notation. Oh, it's so rich. I love it. H prime of 6. I'm declaring a function, H prime. Giving them the variable, the independent variable time. Oh, it's at 6. So much stuff. You're going to grow so much mathematically. It's exciting. All right. The following table, this was in our textbook. Without calculus, with calculus, things that we can do with calculus that we couldn't do before. So before we had slope of a line. Now we're going to talk about the slope at a precise point. This was over 2 time intervals. We're talking about the slope at a particular point. And that was the practice we were doing today. We're going to talk about the value of c. I can also talk about what the function approaches at time c. That's the idea of a limit. Secant lines, tangent lines. Secant, I can get the average rate of change of a secant line. Can I get the slope? I'm going to put an M there for slope. The slope of a tangent line. Average rate of a car. We started out our lesson today on that. Instantaneous. What happened at 5 seconds? Not at from 5 seconds to 6 seconds. The curvature of a circle and the curvature of a curve. Just all kinds of things we can do. We can talk about, where's my one? I can talk about the volume of that object. It looks kind of like a flower vase. We weren't able to do that before. We could talk about volume of polyhedrons. There we go. Polygons. No, polyhedrons. 3D objects, right? But they had to be nice. They had to be cubes, prisms, triangular prisms, cylinders. How do you get it for a vase? So all kinds of fun things coming our way because calculus is the study of change. You have some studying to do tonight. There is homework that is being assigned, and it is, I think there's 4 questions. It's multiple choice. So walk through, use this notion of slope at a point, okay, that we did in our lesson today to help walk you through this. So good luck. Nice to meet you. And we are off and running.